All right, open up your book to section 12-7. We're on page 640 in your book. And the title of this section is Direction Angles and Direction Cosines, and our objective is given a vector. You want to be able to find its direction angles, and you want to find the direction cosines, and vice versa. If you recall back at the beginning of this chapter when we started looking at vectors in three-dimensional space, we talked about how to find the magnitude of those vectors, and we said that the direction of those vectors was a topic for a later discussion, and we've now arrived at that point. This is the later discussion about how to find the angles of those vectors. All right, so let's start with direction angles. You'll notice first of all that it's plural, which means that we're going to be finding the angle using more than one angle to define a vector in three-dimensional space, unlike in two-dimensional space where we only use one angle. So let's start with a vector here. I've got a vector marked here in red. That's vector v. And vector v over there on the right is just, we're going to define that as the position vector x times the unit vector I plus y times the unit vector j plus z times the unit vector k. So it's got its tail at the origin and it's got its head there at the point x, y, z in the coordinate plane. And we've got our x, y, and z axes sketched here. We've got a bounding box here just to kind of give this some perspective of this vector in three-dimensional space. But the critical part for us to talk about right now is the angles that we measure. We measure the angle between the x-axis and our vector, and we call that angle alpha. That's the Greek letter alpha. And then we measure the angle between the y-axis and our vector, and we call that angle beta. That's the Greek letter beta. And then finally, we measure the angle between our vector, between the z-axis and our vector, and we measure that and call that angle gamma. So that's the Greek letter gamma. So we have alpha, beta, and gamma are our three direction angles for a vector in three-dimensional space. Again, it's not a direction angle, singular, but rather direction angles. It's plural because there's actually three of them that we need to uniquely define a vector in three-dimensional space. And once you have those three angles there, that uniquely defines your vector for you. So again, those three angles there, just to put it down in writing here for us, the angle between the x-axis and our vector v is gamma. Notice, by the way, that the x-axis is also in the same direction as our unit vector I. So saying it's between the x-axis or the unit vector I, and v is the same thing. For beta, again, that's the angle between the y-axis, or that'd be the same as the unit vector j and vector v. And finally, gamma is the angle between the z-axis, or that would be the unit vector k, and vector v. Now, if we're talking about finding angles between the x-axis, for example, or the unit vector I, and some vector out there, if you recall back to how we've discussed how to find angles between vectors, we've really now seen two ways that you could possibly do that. One, both of them involve products of vectors. One is a dot product, which is the preferable method, but you can also use the cross product. Remember, the magnitude of the cross product involves the angle, the sine of the angle between the two vectors. So you have two ways you could find these angles. I'd suggest to you that the dot product is a much better approach here. In fact, that's how we're going to define the direction angles here. If you go back and refresh your memory on how you find the dot product of two vectors, this formula will emerge when you solve for the angle. We can remind ourselves of that here real quick, but if we're trying to find the dot product between two vectors, like let's say we have vector A and vector B. So if I want to find vector A dotted with vector B, remember you find the magnitude of your two vectors. So it's the magnitude of A times the magnitude of vector B. And then you multiply that by the cosine of theta, where theta is the angle between the two vectors. So if we just take this formula here and we solve it for the angle, solve it for theta, like you've done for a number of problems now, this little formula will emerge here. So alpha, it turns out, is equal to, it's the angle between vector v and vector I. Again, that's the x-axis, or that runs in the same direction as the positive x-axis. So it's the dot product of v and I divided by the magnitudes of v and I. Now, if you consider what v dotted with I is equal to, we can remind ourselves of how we've defined these vectors here. We said that vector v was equal to x times vector I plus y times vector j plus z times vector k. We defined that up above. And vector I, well, vector I has only an x direction to it, so it's really a 1 times x or 1 times I here, and then it has nothing for the j and the k, so it's 0 times j and 0 times k. And so if you go ahead and find the dot product of these, you'll find that, of course, when you take x times 1, you just get x. When you take y times the 0, those cancel out. Z times 0, those cancel out. So really, the dot product just turns out to be this quantity right here, x. And that's what we're seeing in the formula there. The dot product of v dotted with I, we can just simplify that to just x. And still divided by the magnitude of v. Again, the magnitude of I, since this is a unit vector down here, its magnitude is 1. So we can just replace the magnitude of I with 1, which is what it's equal to. And we simplify this to this little formula here. It turns out that to find the direction angle for alpha, it's just the cosine inverse of x over the magnitude of your vector. For beta, same story, but it'll be y divided by the magnitude of your vector. And for gamma, it'll be z times the magnitude of our vector. So it turns out to be a really nice little formula there that we can use to find those 3 direction angles. All in terms of the components, x, y, and z, divided by their magnitude, and then take the cosine inverse. All right, the other half to this story here then is the direction cosines. And the direction cosines might, if you think of the formula that we just looked at on the previous slide, that probably is a dead giveaway as to what we are going to be talking about with direction cosines, but it's just another way to rewrite the quantities that we had on the previous slide there, but instead of finding what the angle is, you find what the cosine of the angle is. So given the position vector v, which is equal to x times your unit vector I plus y times our unit vector j plus z times our unit vector k, so same position vector that we were talking about on the previous slide. It turns out that the cosine of alpha, we define that as C1, and that is just going to be then equal to x over the magnitude of vector v. Again, look at the previous slide, and that shows you directly where these little formulas are coming from. For C2 we call the cosine of beta. That's our direction cosine for beta, and that's y over the magnitude of vector v. And finally, for C3 is the cosine of gamma, which is z over the magnitude of vector v. Now, there are some interesting properties that develop from these direction cosines. And the first one here is what we call our Pythagorean property, and named, from, of course, because of the Pythagorean theorem. But the Pythagorean property says this, that if you take the direction cosine for alpha, so that's cosine, and square it, so that's cosine of alpha squared, and add it to the direction angle for beta, or sorry, the direction cosine for beta, and square it, so that'd be the cosine of beta squared, and do the same thing for gamma, so the cosine of gamma squared, it turns out that that sum gives us 1. So this isn't quite the Pythagorean theorem there, but it's pretty close to the Pythagorean theorem, or you can see where it comes from as to why we call it the Pythagorean property. Another way to write this then, because we called the cosine of alpha C1, that's just C1 squared then, and because we call cosine of beta C2, we could write that as cosine, or sorry, as C2 squared. And again, cosine of gamma, we called that C3 up above, so we could write this as C3 squared, and that sum again turns out to be 1. It's pretty easy to show this property, by the way, if you want to look at where this property comes from. If you go back up here and look at how we define C1, C2, and C3 and square each of those, you'll quickly see where this property comes from here. But if I take C1 and I square it, so I have C1 and I square it, that's just going to be just this x over the magnitude of v squared. So that's x over the magnitude of vector v squared. So you can simplify that. Of course, just x in the numerator would just be x squared. And remember, to find the magnitude of a vector, you just simply take the square root of the components there. And remember that vector v, we define that up above here. That's just x, y, and z are the components of it. So this is the square root of x squared plus y squared plus z squared. And again, it's that quantity, the magnitude squared. So we're squaring this guy right here. Well, if you take that square root and you square it, then of course that square root just really drops out of there is what happens. So we have just x squared divided by x squared plus y squared plus z squared. And that's what C1 squared turns out to be. We can do the same thing for C2 if we square it. You'll end up with this, going through the same process there. You're going to end up with y squared divided by x squared plus y squared plus z squared. And finally, if you take C3 and you square it, you're going to get z squared divided by x squared plus y squared plus z squared. And if you add these three quantities together, they already have a common denominator. If you add them together, you'll see that the numerator turns out to be x squared plus y squared plus z squared, which is the same as the denominator, which means that you end up with 1. So that's where that property comes from there. It is, in essence, kind of like a Pythagorean property that we have for this. And the other property that we have is the unit vector property. If we're trying to find a unit vector in the direction of vector v, again, you got to go back to the beginning of this chapter. We talked about how to do that. But to find a unit vector, you just take the vector and you divide it by its magnitude. So if we take vector v, for example, that we're working with, divided by its magnitude, now we have a unit vector that's in the direction of vector v. So that vector v there we defined up above as xi plus yj plus zk divided by its magnitude. And you could split this up. You could take each of these terms in the numerator and divide it by that denominator. So I could write this as x over the magnitude of v. Those are both scalar quantities, so we put that as some scalar times I. And do the same thing for y over the magnitude of vector v times j. And finally do the same thing for z over the magnitude of vector v times k. Well, we just defined these quantities up above there. X divided by the magnitude of vector v was the direction cosines. So x over the magnitude of vector v, that's the cosine of alpha times I. And y over the magnitude of vector v, that's just the cosine of beta times j. And finally, z over the magnitude of vector v, that's just the cosine of gamma times vector k. Or if you want to write it in terms of those abbreviations there, C1, C2, and C3, you could write it that way as well. Vector u is equal to C1 times I plus C2 times j plus C3 times k. So if we know the direction cosines of our vector, we can very quickly come up with a unit vector that lies in that direction. You just simply use those three as the three components, and there you go. You've got yourself a unit vector that's in that direction. All right, let's take a look at a couple of examples here. Let's start with example 1 here. It says find the direction cosines and the direction angles for vector v here. So they've given us vector v, and they're saying that vector v is equal to, it's 3i plus 7j and 5k plus 5k. Yeah, do that a little bit better here. Okay, so there's our vector v, and we just want to find the direction cosines and then the direction angles. And I'm going to suggest that we do it in the order they say there, although technically it doesn't matter, but I think it's more natural to first find the direction cosines, and then you can solve that to find the direction angles. So the direction cosines, remember that we need to know the magnitude of this vector. So let's first start out by finding the magnitude of vector v. And that's just going to be the square root of 3 squared plus the 7 squared plus the 5 squared. So what do we end up with? A 9 and 49. 49 is 58 and 25. That sounds like 83. So square root of 83 is what we should have here. So our magnitude is the square root of 83. So if we want to find the direction cosines, we can say that the cosine of alpha is equal to, we just take the x component divided by the magnitude that we got here. So this is just 3 divided by the square root of 83. And for beta, cosine of beta, that's just the y component, so that's 7 divided by the magnitude, so that's the square root of 83. And for the gamma, cosine of gamma, is equal to, that's the z, that's 5 divided by the magnitude. There we go. That's not too bad to come up with. Those are pretty easy. We just need the magnitude of our vector. If we're given the vector in component form, we can actually come up with those direction cosines pretty quickly here. And then to find what the direction angles are, we just have to solve for the angles. So I just got to take the cosine inverse of all these. So if I take alpha, alpha is going to be the cosine inverse of the 3 over the square root of 83. And for beta, we'll punch these in our calculator in just a second, but let's go ahead and write down what the 3 of these are. That's going to be 7 over the square root of 83. And for gamma, that's the cosine inverse of 5 over the square root of 83. All right, so grab your calculator and let's punch those in and see what angles we end up with. All right, so if we take our 3 direction cosines here and just find the angles there, the cosine inverse of those quantities, we'll end up with our 3 direction angles. So if I take the cosine inverse of 3 over the square root of 83 was our first one. That's our alpha. And we'll do that again. But this time we're going to use 7 for beta. And do that one more time, but this time use 5 to find gamma. So those are our 3 direction angles there. Let me just grab a picture of that. Just put it over here for right now so I can write those numbers down, and I'll move it in a second. All right, so for alpha, our direction angle turned out to be all right, so for alpha, we have 70.774. Make sure you're putting 3 decimal places here in your answers. For beta, we have 39.794. And for gamma, we have 56.17 or 714 if we round that to 3 decimal places. Those are our alpha, beta, and gamma there for our 3 direction angles. All right, take a look at example 2. Example 2 on page 642 now says find the direction angles and direction cosines of this vector. So they've given us a new vector here to work with. Vector v is equal to 13i minus 6j plus 18k. So this is going to ask us to do something similar to the previous one. They want us to find the direction angles and direction cosines here. We're going to do the direction cosines first though. But then it also says use the result to find a unit vector. But again, once we find our direction cosines, remember we can do that pretty quick. So the first thing we need to do is find the magnitude of vector v. So the magnitude of vector v, that's going to be the square root of 13 squared plus a negative 6 squared plus 18 squared. And what do we end up with? That's the square root of 529, which actually is a pretty nice number. That turns out to be just 23. So you can punch that in your calculator and double check that that's the number you end up with, but that's what we should have there as our magnitude of vector v. So now for your direction direction cosines, let's start out with alpha. So the cosine of alpha is equal to, it's going to be 13 divided by the 23. It's just the x value divided by the magnitude of the vector that we just found. And for the cosine of beta, that's going to be equal to a -6 divided by this 23 as our magnitude. And finally, for the gamma, cosine of gamma is equal to 18 divided by 23. All right, and if we want to find the direction angles for these three, we can do that by just simply finding the cosine inverse of those quantities. So for alpha and beta and gamma, this is going to be the cosine inverse of 13 divided by 23, and the cosine inverse of a -6 over 23, and finally the cosine inverse of 18 over 23. And let's go ahead and punch those in our calculator just so we can see what those are equal to in terms of their direction angles. All right, so the first one there was the cosine inverse for alpha, cosine inverse of 13 over 23. And then we'll just modify that there slightly. For the beta, it's going to be a -6 over 23, we said. And for gamma, it was 18 over that 23. So there's our three direction angles there. Again, we grab a picture of that. And we'll paste it in over here. All right, so it turns out that for alpha, we had 55.583. We'll round that. Again, make sure you're putting 3 decimal places here on all your answers. 105.122 is beta, and finally 38.4. I guess if we round that, it's going to be 500. That's in degrees there when we round it 3 decimal places. All right, so those are our 3 direction angles and 3 cosine angles. Let me move this out of the way here. The question, though, also asked us to find our unit vector. So to find our unit vector, that just means that we have to take our direction cosines and write that as a vector, really, the components of a vector. So our unit vector, we'll call it u. Vector u is equal to, I can just steal these direction cosines here. We said it's 13 over 23 times vector I plus a -6, or you could write that as -6 over 23, however you want to write it, times vector j, and finally 18 over 23, oops, times vector k there. There we go. There's a unit vector in the direction of vector v that they gave us. All right, one last example here on page 642. It says if alpha is equal to 152 degrees and beta is 73 degrees, find gamma. So in the previous example there, we used one of our properties, our unit vector properties, for our direction cosines, and it looks like we're going to have to use another property here for this, or the other property, I should say, for this one. Again, alpha was 152 degrees, and beta, they said, was equal to 73 degrees. And the question is, what does gamma equal? And so to find that, we had a Pythagorean property that we can use to actually help us find out what gamma is equal to. I should say we can come up with 2 possibilities for what gamma is equal to. So our Pythagorean property said that if I take the cosine of these direction angles, so if I find the direction cosines and square those and add them up, I'll end up with 1. So I can take the cosine squared of 152 degrees, and I can add that to the cosine squared of 73 degrees, and add that to the cosine squared of gamma, that's the quantity we're looking for, and set that equal to 1. So I only have one unknown in here, which is gamma. So let's solve for that. The cosine squared of gamma is equal to, it's going to be 1 minus, let's move these other two quantities to the other side, 1 minus the cosine squared of 152 degrees, and then minus the cosine squared of 73 degrees. And again, since it's cosine squared here, to solve for cosine of gamma, really we're trying to solve for gamma, I have to take the square root of both sides. And to take the square root of both sides there, don't forget you got a plus or minus that's going to show up. So I've got the cosine of gamma is equal to plus or minus the square root of all this, 1 minus cosine squared of 152 degrees minus the cosine squared of 73 degrees. And then finally, to find what gamma is equal to, I have to take the cosine inverse of those two quantities, cosine inverse of the positive quantity and the cosine inverse of a negative quantity. So let's go ahead and grab our calculator and punch that in and see what we end up with. All right, so on your calculator, let's just take the square root of this whole thing here, 1 minus the cosine of 152, and again, we're squaring that, so don't forget to square that, and then minus the cosine of 73 was our value for beta, and squaring that. And so we end up with 0.367, and so I need to take the cosine inverse of that quantity and the cosine inverse of the opposite of that quantity is what I need to do here. Let me just store this into, since this is gamma, I'm going to store that into g, so just so I have that value and I can find the two quantities I need here. I need the cosine inverse of that value of g, and I need the cosine inverse of the opposite of that value. And so we get 68.449 and 111.550. Those should look like they're related there to you. Hopefully you notice that the sum of those is 180 degrees. That's the property we know from cosine that we'd end up with here, but they're supplementary. So let's grab a picture of that. Paste that in here so we can copy down our answers. Again, we have two possible answers here because the fact that this vector could be pointed in two directions here from just giving two quantities, that is given just the alpha and the beta. That does not uniquely define the vector. That's why we need all three of these. So gamma turned out to be 68.449. I guess it's going to be 450 if we round that. You can truncate it as well. And the other solution is its supplement, 111.550 degrees. And those are the two possible direction angles for gamma.